In this subtopic of chemical bonding, we're going to talk about Lewis structures. So Lewis structures are useful in indicating the bonding between molecules. There are specific rules that we need to respect when we're talking about Lewis structures. The first one is that all valence electrons must appear in a Lewis structure. The second one is that electrons are usually paired in Lewis structures. The third rule is that valence shells are usually filled. And the fourth one is that multiple covalent bonds are often needed, especially in the cases of carbon, nitrogen, oxygen, phosphorus, and sulfur. So let's start by skeletal structures. Skeletal structures is considered to be the starting point in writing the Lewis structure for a molecule. So when I say skeletal structure, it means that you're only showing the bonds between the atoms. You're not showing any valence electrons or whatsoever. The only thing that shows in the figure is the single bonds, or double bonds, or triple bonds. So only the bonds are shown in the figure. In skeletal structure with more than two atoms, we have two types of atoms. We have a central atom, which is bonded to two or more atoms, and a terminal atom that is bonded to just one other atom. So if we look at this figure for ethanol, we could see here that we have three central atoms, C, carbon, carbon, and an oxygen. And we have 1, 2, 3, 4, 5, 6 H's, which are terminal atoms. So again, central atoms are bonded to two or more atoms. There are some specific rules for skeletal structures, and specifically of in naming central atoms and terminal atoms. So the way you draw a skeletal structure, there's actually four rules that you have to abide by in order to draw a skeletal structure. The first rule says that hydrogen atoms are always terminal atoms. Well, the reason for that is because they can only accommodate two electrons in their valence shell. As we all know, that the Lewis structure for hydrogen is simply like this. So it can only accommodate one more electron in its valence shell, and therefore it's most of the time a term. In all the times, actually, it's always a terminal atom. Central atoms are generally those with the lowest electronegativity. So usually the central atom, the one in the middle, has the lowest electronegativity. There's of course exception to this rule, and one of the exceptions is the oxygen atom, which can be in some specific structures a central atom. There's two structures in which the oxygen serves as a central atom. One of them is through a peroxo linkage, and you could see in this case. So we have a two oxygen bonded with oxygen, and in this case, one of them is a central atom. Or we have the oxygen in a hydroxy group, and for a hydroxy group, the oxygen atom can serve as a central atom as well. Otherwise, so other than those two cases, an oxygen is always a terminal atom. The third rule for skeletal structures is carbon atoms are always central atoms. Remember, carbon atoms have 4 electrons in their valence shell. So they can actually bind the most to other atoms. So they can bind to 4. They have the capability of binding to 4 other atoms. And the fourth rule we have to know is that generally molecules and polyatomic ions have structures that are compact and symmetrical. So generally, when we're doing skeletal structures, molecules and polyatomic ions have structures that are compact and symmetrical. An exception to this rule would be a very large number of chain-like organic molecules. So usually organic molecules do not have a compact and symmetrical structure. Now, of course, when drawing the skeletal structure, a compact structure is the most likely structure. So you might actually, we're going to do some examples in the example section where we're going to show you some compounds where you have to decide which skeletal structure is the right one. And this depends on whether we are drawing the most compact figure representing the compound, or is it just the most spread out sort of structure for the compound? So how to start drawing a Lewis structure? So here we're going to go through the steps of how to draw a Lewis structure. So first things first, you check if the compound is ionic. And if it is ionic, treat each ion separately. So remember, in ionic compounds, the ions are not actually connected physically to each other. They're at a distance from each other because the electron is transferred to the other atom, but they're not actually, there's no specific bond such as covalent bond between them. The second step is to add up the number of valence electrons. So you add up all the number of valence electrons in all the compounds. So let's say you have CO2, carbon has 4 valence electrons, oxygen has 6. So we have CO2, then this would be 4 plus 6 plus 6. So that's the first step. You add up the number of valence electrons. Add or subtract electrons to give the right charge. This is available. So you have to add or subtract electrons to give the right charge. Now, at this step now, we need to make sure that we have the right charge for the compound. And we're going to go through the steps in an example soon. So the available electrons that are left with, so we have available electrons, we have electrons that are present in lone pairs. Each one is abbreviated in a different letter. So the available electrons is A. Now at this point we draw a skeletal structure. So a structure just representing the bonds between the atoms. The central atom will normally have the lowest electronegativity. Carbon is always a central atom and hydrogen is always a terminal atom. Fourth step, calculate the number of valence electrons needed to give all atoms a full shell. So the first thing we did was calculate the number of valence electrons that we have. The second thing we do is calculate the number of valence electrons needed to give all atoms a full shell. So it's either going to be 2 or 8. Now we're going to talk about other exceptions later, but for now, focus on giving each atom either 2 or 8. Of course, 2 is for the hydrogen atom. 8 is for other elements. Now, the number of needed electrons is represented by n. Now, after knowing what available electrons is, the number of available electrons, and the number of needed electrons is, we have to determine the number of electrons that must be shared. And the electrons that must be shared is represented by S, and it's equal to the number of needed electrons minus the ones available. The sixth step, place single bonds in the skeletal structure, 2 electrons per atom. 2 electron pairs, sorry. So at this stage now, a single bond represents 2 electrons. So when you count a single bond, you count 2 electrons. Now you keep adding extra bonds until you satisfy S. So S is the number of electrons that needs to be shared. After you satisfy S, then place the remaining electrons in lone pairs to complete the octet for each atom. So the first thing is we have to connect the atoms together. After connecting the atoms together, we count how many electrons we have through the single bonds. And remember, each single bond is 2 electrons. And then add extra bonds to satisfy S. After satisfying S, place the remaining electrons in lone pairs to complete the octet rule for each of the atoms. So let's we're going to give you an example now of cyanogen. Cyanogen is represented by C2N2. So first things first, this is not an ionic compound, so we don't have to treat it as an ionic compound. The carbon over here has 4 valence electrons. The nitrogen has 5. So A in this case, which is the electrons available, is 4 times 2 because we have 2 carbons, and then 5 times 2 because we have 2 nitrogens. And this adds up to 18 electrons. Each atom wants an octet. So the numbers that we need, each atom over here requires 8 electrons to be full. Therefore, we have four atoms, so 4 times 8, and that gives you 32. Now, the shared electrons, which is represented by S, is 32 minus 18. So it's 32, it's N minus A, and it's equal to 32 minus 18, which is equal to 14. So now that we know the shared electrons, let's see how many bonds those shared electrons represent. So we know that each bond is represented by 2 electrons. Therefore, we can divide the number S, which is 14, by 2 in order to get the number of bonds. And in this case, we get 7 bonds. Now, at this point, we can actually draw the skeleton structure. Now, when drawing the skeletal structure, of course, we have to know what is the central atom. In this case, we compare the electronegativities of C and N. We find that C is less electronegative than N, but still, central carbon, the carbon is usually the central atom, so we use the carbon as central atom. So after connecting the atoms together with a single bond, we still need 4 more bonds in order to satisfy all the atoms. Now, when we add the bonds in order to satisfy the S, remember we have 7 bonds in order to satisfy S. We already linked 3, we still have 4. So now how are we going to do that? The only way to satisfy S is by doing an extra 2 bonds over here and an extra 2 bonds here. So this way, a triple bond is present between the C and N, and another triple bond is present between C and N. So this is the only way to add 4 bonds without having more than 8 electrons around the carbon. Now, after adding those single bonds, this uses 14 out of the 18 electrons that we initially had. So we have 4 electrons left. The carbons have their octet already satisfied, but each nitrogen is two electrons short from the octet rule. So this means that each nitrogen will get lone pair. And then you can have the structure like this. We're going to talk now about formal charges. So the formal charge are apparent charges on certain atoms in the Lewis structure that arise when atoms have not contributed equal numbers of electrons to the covalent bonds joining them. So sometimes we have a charge on an atom. This is because the atoms in let's say the specific Lewis structure do not contribute equal numbers of electrons to the covalent bonds that are present. So we have to represent this formal charge on those atoms, because Lewis structure alone does not actually tell us which electron came from which atom. It simply just shows us a figure with all the electrons bonded and the lone pairs. So this formal charge actually tells us which electron came from where. The method of obtaining the Lewis structures does not keep track of where the electrons came from. This is why the formal charge is important. So in calculating the formal charge, there is a specific sort of equation for it. The equation goes by the group number of the element you're studying, or the atom you're studying. So the group number signifies the number of valence electrons in the neutral atom. So let's say for carbon, that would be 4, because carbon has 4 valence electrons and it's a neutral atom. Now this group number, and then you have it subtract half the number of electrons in covalent bonds. So remember, the covalent bonds, the electrons in the covalent bonds are shared. So they're actually 2 electrons. Each bond represents 2 electrons. We divided by half in order to just get into account only one of those electrons, because the other electron is going to be calculated in the formal charge for the other atom. And then we also subtract the number of electrons in lone pairs. But for the number of electrons in lone pairs, we don't multiply by half, because the lone pairs are for one specific atom. They're not shared by the other atom. So we could write it like this, or we could write formal charge as a group number minus number of covalent bonds minus number of electrons in lone pairs. So here we said the number of electrons in covalent bonds. That's because each bond represents 2 electrons. So if you count each bond as 2, then you have to divide it by half. But if you calculate the number of covalent bonds, then you don't actually have to multiply by half because it's already been done for you. So there are specific rules for formal charges. The most plausible rule is the one where no atoms, the most plausible structure is where no atoms have a formal charge. So you want to try to find a structure, or sort of like a structure that where atoms do not have formal charges. So the main goal is to find the structure that has the least formal charge present. Where formal charges are required, they should be as small as possible. So you should always aim for a smaller formal charge. You should try to accommodate, or try to change the shape of the molecule in order to accommodate for the least amount possible for a formal charge. The third rule is that negative formal charges should be on the most electronegative atoms. So electronegative atoms are the ones that attract the most, the ones that attract electrons the most. So it would make sense if they have a negative formal charge. So it is really important that you locate the formal charge, the right formal charge on the right atom. So if we have an atom that is highly electronegative, it's not realistic for us to put a positive formal charge on it. So we have to try to accommodate all the electronegativities of the atoms present in the molecule in order to sort of create this whole reasonable formal charge for it. The fourth rule is that same sign formal charges on adjacent atoms are unlikely. So it's really unlikely that we have a positive formal charge atom bound to a positive formal charge atom. So you know how positive and negative attract, positive and positive repel each other. So that sort of, think about formal charge in the same way. It's really difficult to actually make two atoms that have both positive formal charges to attract each other and bind. Therefore, it's more likely to have a negative formal charge atom next to a positive formal charge atom. Let's go through some examples. This here is nitrogen dioxide. And in the case of nitrogen dioxide, the formal charge of oxygen, so we have the first one is the valence electrons. Oxygen has 6 valence electrons. The next step is to count the electrons in the lone pairs. Oxygen in this case has 1, 2, 3, 4. So 4 lone pairs. 4 electrons in lone pairs. And then the third step is to calculate the electrons in covalent bonds. And in this case, we have 1, 2, 3, 4 electrons, and then we multiply it by half so we can count for the covalent bonds. Remember, each 2 electrons provide us with one covalent bond. So the formal charge of oxygen is 0. Now, on the other hand, the formal charge of nitrogen, we have 5 valence electrons. Nitrogen in this case has no lone pairs, and in this case, because we have 1, 2, 3, 4, 5, 6, 7, 8, we have 8 electrons in total bound by covalent bonds. Multiply this by half, and then if you do the addition for this, you will get plus 1. So in this case, the formal charge of plus 1 is present on the nitrogen, which makes sense. And the formal charge on oxygen is 0. So this is the least sort of formal charge that can be present on those 2 atoms. This example over here, nitrosyl chloride, is a more detailed example just to show you how it's done. So on nitrosyl chloride, let's talk first about this side. So the chlorine and the nitrogen donate 1 electron each. So you can see here there's 1 single covalent bond between them. And the ON donate 2 electrons each. So donate 2 electrons each. Now, this sort of configuration seems reasonable because, first of all, they're all satisfied. And it makes sense because the oxygen had 2 unpaired electrons that now are shared. So it has full octet. This one has full octet, and this one has full octet. Now in this other case, chlorine donates 3 electrons to the bond. O donates 0 electrons to the bond. So we have this one single bond over here, and then 3 lone pairs for the oxygen. So let's calculate now the formal charges in both cases and see which one actually is more reasonable. So the formal charge in the first one, for the oxygen we have 6 valence electrons, and we have over here 4 electrons in lone pairs, and then we have 2 covalent bonds. So that comes up to 0 formal charge. The nitrogen now has 5 valence electrons, 2 electrons in lone pairs, and 3 covalent bonds. That comes up to 0 formal charge. The last one, the chlorine, has 7 valence electrons, 6 electrons in a lone pair, and 1 electron that is shared. So it comes up to 0. So in this case, we have 0, 0, 0 as formal charge. Let's see the other scenario, in which we have a double bond between chlorine and nitrogen, and single bond between nitrogen and oxygen. The formal charge on oxygen in this case is -1. Do the same calculation, of course, as what you see over here. You get -1. And for the nitrogen, you have 0. And for the chlorine, you have over here +1. So now in this case, let's see what does not fit into this rule. So the most plausible structure is the one where no atoms have a formal charge. So the first scenario fits this, but the second doesn't. Where formal charges are required, they should be as small as possible. That does not relate to our situation in here. Well, it does relate, as in we have in the first scenario 0, 0, 0 formal charge, and the other one we have -1 and +1 for chlorine. Negative formal charges should be on the most electronegative atoms. So if we go to the periodic table, we could see that chlorine is more electronegative than oxygen. And in this case, chlorine has +1 and oxygen has -1, which does not make sense, because when you compare the electronegativity, chlorine is more electronegative, so you'd expect it to have a negative formal charge. And finally, same sign formal charges on adjacent atoms are unlikely. Now in this one, it does not actually relate to us, because nitrogen over here has 0, and this one has plus, and this one has minus. But as you could see, that the first scenario over here agrees with 3 of the rules that are given to formal charges, while the other one does not agree with any of the rules for the formal charge. So this is how you decide which sort of configuration or structure is the most reasonable structure. So again, you do the lowest structure. You make sure you drew the lowest structure. For specific compounds, you might have more than one type of lowest structure. You can have more than one scenario of low structure. How you decide which one is the most right one is by doing a formal charge. So when you do the formal charges, you can find out which one is the most reasonable lowest structure to represent the compound. The last topic we're going to talk about in lowest structure is resonance. So consider ozone 3 over here. You could see here we have 3 oxygens. One time it's represented like this, and the other time it's represented like this. Now, each structure suggests that one oxygen to oxygen bond is single and the other is double. Just by looking at it, that's what it suggests. But experimental evidence shows that bonds are of the same length. So when scientists did experiments to see the bond length for ozone, they saw that the bond length for those are actually the same length. So how does this make sense? We know that when we have double bonds, usually the lengths are smaller. So when you have a double bond between 2 atoms, the bond length becomes smaller. So how come that the single bond in this case and the double bond have the same length? Well, scientists suggested that some molecules have a hybrid structure, What do I mean by hybrid structure? This means that there's an intermediate structure in between those two, in which we have a sort of intermediate between a double and a single bond. And resonance in this case, which represents hybrid molecules, it can be shown like this. So you could write both structures and you could have an arrow between them that's double-sided. And when you have this double-sided arrow, this means there's a resonance between those two molecules. In this case, it can be said that the oxygen to oxygen bonds in ozone are halfway between a single and a double, and they are represented by 1.5 bonds. So instead of saying one bond single and one bond double and a double bond, we have 1.5 bonds between the oxygens.